Hi, I'm Jeff Groh, and this is Differential Equations, Lecture 8. Today we're going to talk about the Cauchy-Euler Equidimensional Equations. These have the form ax squared y double prime plus bx y prime plus cy equals f of x. And in particular, we are going to consider the homogeneous case. We begin by making a reasonable hypothesis. All of the coefficients are powers of x. So we're going to suppose that the solution is of the form x to the power r for some real number r. If that's the case, then the derivative is r, x to the r minus 1, and the second order derivative is r times r minus 1, x to the r minus 2. Plugging these into the homogeneous differential equation, we get ax squared times r minus 1, x to the r minus 2, plus b, x, r, x to the r minus 1, plus c, x to the r equals 0. X squared times x to the r minus 2 equals x to the power r because we add the exponents. Similarly, x times x to the r minus 1 is also x to the power r. We can see that in all three terms we have x to the power r. What's left over is r minus 1 plus br plus c equals 0. If this equation is to be true for all x, and in particular for x equals 1, it follows then that we get an equation r minus 1 plus br plus c equals 0. Rearranging terms a little bit in the last equation was r minus 1 plus br plus c equals 0, which we can call perhaps the characteristic equation for this sort of problem. We'll have ar squared. We'll have a negative ar and a positive br. I'll write that as b minus ar, and then the only constant term is c, equal to 0. You can see then that this has solutions using the quadratic formula of negative b minus a plus or minus the square root of b minus a quantity squared minus 4ac all over 2a. This gives us three cases. We have case 1, real distinct, R1 and R2, case 2, complex, conjugates, and case 3, real repeated. And we have to handle each of these cases separately. Case 1 is very simple. By the theory that we've developed so far, for case 1, the homogeneous solution will be C1 x to the R1 plus C2 x to the R2 for the real distinct roots R1 and R2 of the characteristic equation. For case 2, we have a plus or minus r alpha plus or minus beta I, where I is the imaginary unit. If I have x to the power alpha plus beta I, we can express that as x to the power alpha times x to the power beta I. So x to the power alpha is no problem. What is x to the power beta I? To figure that out, we'll use e to the log of x to the power beta I. As you can see, we can bring the beta I out front of the log using properties of properties of logs. That's x to the alpha, e to the beta I, natural log of x. It's at this point we use Euler's formula. You'll recall Euler's formula e to the power I theta is cosine theta plus I sine theta. This gives us x to the power alpha times cosine beta times the natural log of x plus I times the sine of beta times the natural log of x. And that is one of our solutions. At least we have a solution. But the problem with this solution is that it is complex valued. However, we've done this, we've played this game before. We know what to do. There's another solution from the complex conjugate root to the characteristic equation. We simply replace beta by negative beta. Remember that cosine is even, so that when we replace beta by negative beta here, we get the negative just disappearing. However, sine is odd, and hence negatives come out. So the complex conjugate yields the solution x to the alpha cosine beta natural log of x minus I sine beta natural log of x. Both of these solutions being complex valued. But we know how to play this game. We'll set W1 to be the average of these two. This gives us x to the alpha cosine beta natural log of x. Similarly, we can set W2 to be the difference divided by 2I, giving us x to the alpha sine beta natural log of x. W1 and W2 give us two linearly independent solutions to the original Cauchy-Euler homogeneous equation. Before proceeding to the third case, I'd like to give a couple examples for the cases that we've already discussed. Suppose we have, for instance, x squared y double prime plus 5x y prime plus 3y equals 0. In this case, the characteristic equation is 1, well, a is 1, b is 5, and c is 3. We will have 1 times r squared. We did b minus a, that's 5 minus 1 r, plus c equals 0. This gives us r squared plus 4r plus 3 equals 0, and that factors as r plus 3 times r plus 1. We get an r1 equals negative 1, r2 equals negative 3, and hence the solution is c1 x to the power negative 1 plus c2 x to the power negative 3. For another example, let's consider x squared y double prime plus 5x y prime plus 13y equals 0. The characteristic equation is 0 equals r squared plus 5 minus 1r plus 13, or r squared plus 4r plus 13. It might be easier to solve this using completing the square method than the quadratic formula. To complete the square, you divide this by 2, divide 4 by 2 and square it. That would be 4. You want r squared plus 4r plus 4, not plus 13. So you split this into plus 4 plus 9, and then group the first three terms to get r plus 2 quantity squared plus 9. Bringing the 9 over gives you a negative 9, and so that when you take the square root, you get plus or minus 3 times the imaginary unit I. That gives you two solutions, negative 2 plus or minus 3i. The solution is then y equals c1 x to the minus 2 cosine of 3 times the natural log of x plus c2 x to the minus 2 sine of 3 natural log of x. To consider the third case, here we have a repeated root, r, in which case r does solve the characteristic equation by ar, r minus 1 plus br plus c equals 0, but it does so as a repeated root. To be a repeated root means that the quantity under the square root in the quadratic formula solving this is equal to 0. So b squared minus 4ac in this case will be b minus a squared minus 4ac. If that equals 0, then the quadratic formula gives us r is negative b minus a over 2a. That means 2ar equals negative b plus a, or in other words, 2ar plus b minus a is equal to 0. We have a solution, y1 equals x to the power r, where r satisfies this equation here. However, we need a second linearly independent solution. And multiplying by x will give us something linearly independent, but it won't be a solution. And we know it won't be a solution because the only solution of the form x to the power r is the one where r is the one and only solution to the characteristic equation in this case. So x to the r plus 1 or r minus 1 cannot be a solution. So we have to figure out something else. We'll use reduction of order. We know that the solution will look like c1y1 plus c2y2. Reduction of order proceeds by assuming that the coefficient of y1, which is a constant c, is not in fact a constant for y2, it is a function. We'll assume y2 is u times y1. This means that y2 prime is u prime y1 plus u y1 prime, and y2 double prime is u double prime y1 plus 2 u prime y1 prime. We get one of those by taking the derivative of the second factor in the first term, and the other one by taking the derivative of the first factor in the second term in their respective product rules. That leaves only one term, u y1 double prime. We need to plug all of this into the differential equation. This gives us a x squared times u double prime y1 plus 2u prime y1 prime plus u y1 double prime plus bx times u prime y1 plus u y1 prime plus c times u y1. All of this must equal 0. You can see this term, and this term all have a common factor of u, and we can factor that u out, keeping in mind that y1 is a solution to the differential equation. These three terms must cancel out. Also remember that y1 is of the form x to the power r. We get ax squared times u double prime x to the power r plus 2r u prime x to the power r minus 1, and then plus bx u prime x to the power r. This whole thing simplifies as a x to the r plus 2 u double prime plus 2ar x to the r plus 1 u prime, and then plus b x to the r plus 1 u prime, keeping in mind that 2ar plus b must in fact equal a. These equations imply that 0 is a x to the r plus 2 u double prime plus a x to the power r plus 1 u prime. Note that we can factor out x to the power r plus 1, just leaving 0 equals ax u double prime plus a u prime. The a also cancels off. The method reduction of order follows like this. You always end up with an equation that does not involve u, only u prime and u double prime. At this point, you set w equal to u prime so that w prime is u double prime. These two imply then that 0 equals x w prime plus w. This equation is separable. Having reduced everything down to x w prime plus w equals 0, we'll move the w over. We'll get x dw dx equals minus w, and then separating the variables, we get 1 over w dw equals minus 1 over x dx, which we then integrate. We get ln of w, and as you'll see, we don't need the plus c's or the absolute values here. We'll get w as a constant times x to the negative 1 using the property of logs, where this becomes an exponent on the x, and then we exponentiate to get rid of the logs. Again, because we're going to have a constant times our y, this constant is unnecessary at this point. But keep in mind, w is u prime. We still have to integrate again to figure out what u is. With u prime equal to 1 over x, you see that u is the natural log of the absolute value of x, which means that y2 is the natural log of the absolute value of x times x to the power r. You don't multiply by x to get a second linearly independent solution. In this case, you multiply by the natural log of the absolute value. The solution then is y equals c1 x to the r plus c2 natural log absolute value of x times x to the power r. As an example, suppose we have x squared y double prime plus 5xy prime plus 4y equals 0. The characteristic equation is 0 equals r squared plus 5 minus 1r plus 4. If this is 4, then this factors as r plus 2, quantity squared. We get r equals negative 2, but with a repeated root. The general solution then is c1 times x to the negative 2 plus c2 natural log absolute value of x times x to the negative 2. Note that in generating the second linearly independent solution, we don't multiply by x in the Cauchy-Euler case, we multiply by the natural log of the absolute value of x.